Is anyone else weirded out by the fact that abbreviation has 2 B's? I just like, it was in the notes and I didn't even believe it. I had to Google it. I don't think so. No. This is how poorly I spell. Okay, so I think this is where we left off, but I also know in my other class I had like an example of Z effective where we subtracted the core electrons. Did I just do that up here? Is that why it's not on the slide? Okay, I'll do it again, but I'm just hoping that this is a review, not something new. So this is my problem. If I don't do it on the slides, then I can't remember which class I did it in. Okay, so remember, I think we ended with the idea of shielding. Now, we're going to take like this totally different twist in class today, and we're going to talk about how to predict electron configurations without having to go through the whole orbital diagram. The reason why we do that is because it's really important for us to know where the valence electrons are in an atom, and electron configuration will allow us to identify that very quickly. So the examples we had used, I think, were like sodium and chlorine, and then maybe sodium and potassium. So sodium looks like, 1, 2, 3. Sodium looks like this. Okay, so its electron configuration, remember that's where we put the subshell and then how many electrons there are. So 1s2, 2s2, 2p, 1, 2, 2, 4, 6, and then 3s1. Okay? So when we look at the orbital diagram, we can say these guys are the core electrons, and these are the valence electrons. If we have an orbital diagram, that's kind of easy because you can see, where they're physically placed. But if we have an electron configuration, which is much easier to write out, we can identify it simply because we see where the numbers change. Like the core electrons are 1 and 2, the valence electrons are 3. So we're going to explain the shielding thing, we're going to kind of finish up that conversation, and then we're going to swap to electron configurations. And a couple people in the last class were like, how does this connect in with shielding? It's going to by Monday, but we have to talk about electron configurations to get to that point. Okay? All right. So as a reminder, shielding is the idea that the electrons that are in between the valence electrons, so let's say that I'm the 3s electron in sodium, and I've got this 11 protons that I am attracted to. The reason we care so much about the valence electrons is because those are the ones that are going to react chemically, okay? So when I'm talking about this, I'm always picturing it from the valence electrons' point of view. So those 11 protons, I'm attracted to them. However, there's a layer of electrons in the n equals 1, and there's a layer of electrons in the n equals 2, and those really, really inhibit me from feeling that positive charge. So however many electrons there are, we start to kind of cancel out some of that positive charge due to those core electrons. So roughly, this isn't perfect. If we measured these, they would be close to this, but maybe slightly different. What we do is we take the positive charge, so that's Z. Z is always the abbreviation we've used for atomic number or the number of protons. So we take that positive number and we subtract off any core electrons. So for sodium here, which has 11 protons, we subtract off these 10, 2, and then 8, okay? So we say minus 10, and our Z effective is just 1. So that valence electron feels about the same attraction to the nucleus as does hydrogen. Like they're pretty much the same as far as how tightly held they are to the nucleus. And this shouldn't be that surprising. When we go down, or let's actually go up so I don't have to draw as nearly as much. So let's look at lithium. So lithium has 3 protons. These are the core electrons. This is the valence electron. And you might initially think, oh, well, it must be much less attracted because it's only got 3 protons, right? We said the more protons there are, the more those electrons are going to feel that attractive force. But the only electrons that get canceled out are these 2 core electrons, because lithium has the valence electron, and then it just has 1 layer of shielding in that 1s. So we only subtract off 2, and we're left with still that 1 unit of attraction. This actually ends up corresponding to the number of valence electrons. So like if you look at the first column, let me switch over to this. And we'll validate this with electron configurations in a second. But if you look at the first column, those are always going to have 1 valence electron. They will always have 1 electron in the 3s orbital. If you look at the halogens, so that would be like this, they will always have 7 valence electrons, 2 in the 2s and 5 in the 2p. Okay, so that is also kind of connected to this. Not directly because it's the number of electrons, not the number of protons, but it ends up being the same because the core electrons stay constant and the valence electrons stay constant. All right, one more example I want to give onto this before we move on, which means I've got to put back my previous. Okay, so there was sodium, and I want to put up chlorine as well and look at that Z effective. Okay, so chlorine's valence electrons are also at the 3s and the 3p, but they're at n equals 3, just like sodium's are. So these guys are the core electrons, these are the valence electrons. So if we looked at the Z effective, it would be 17 is the number of protons. Still though, we still just have those 10 core electrons. Because we're still at n equals 3, these haven't changed. We have the 1s and the 2s and 2p are our core electrons. So when we look at the Z effective of chlorine, it's positive 7. It's significantly bigger than sodium. And on Monday, we're going to talk about atomic size and how that relates to some other properties about how it'll attract or how easy it will be to remove an electron. And we'll see that simply because chlorine has the same amount of, has more positive charge, but the same amount of shielding, that sucks the electrons in tighter, and you actually see that chlorine is smaller than sodium, simply because of that attractive force that's increased there. Okay, so that's where we're headed with Z effective. But before we can explain that for like every element and kind of identify it quickly, we have to know how many core electrons it has. Okay, we have to know how many principal energy levels do we have in a particular atom. And we could draw out the orbital diagram every single time, but this is kind of like a long way to do it. If you remember, we said electron configurations is a much shorter, quicker way to identify the valence electrons and the core electrons. Okay. okay? So that's what we're going to focus on today. I said that and then I was like, oh, I remember talking about this. Okay, so I wrote Friday there, which makes me think we actually did get to this point. I know we talked about this in chapter 8, but it's just a quick reminder before we get into using the energy of the orbitals the way we did in the orbital diagram, but now using it as text in the electron configurations. Don't forget that the reason why the S is lower in energy than the P, and the S and the P are lower in energy than the D, is because of the shape that they take on and the limited access they have to the nucleus. I'm going to skip over this picture and actually show the one with SD, SP, and D. So the S has these places where it can get really close to the nucleus because of its physical shape, because it's a sphere. The P has a little bit better than the D, but not nearly as good as the S. Again, if we look at this picture from up here, you can see like the electrons can only get about that close to the nucleus and only in those two little regions. And then we don't have a picture of the D on this one, but it's like narrower. There's 4 of them, but they're narrower and they're pulled back from the nucleus a bit. So that makes their energy even higher. The key thing about this that we really care about, because I don't think anybody is bothered anymore by the fact that it goes SPD within a given energy level. What is important to remember is that there is this weirdness between 3D and 4S. So if we look over, I drew the energy diagram. It's on like 2 slides from now if you want to look at it on there. But the layout of the orbitals, it goes by energy level, so 1, 2, 3. And then it goes by the shape, SPD, okay? But when we get to 4S and 3D, we actually start to see that they kind of swap places. So we would always, before this, say, oh, if the N value is less, it's lower in energy. So we should think 3D is much lower in energy than 4S because it's a 3, right? But the shape of the D orbitals is so limiting their ability to get close to the nucleus that the 4S usually ends up lower in energy than the 3D does, okay? They're pretty much very, very close in energy, but kind of the default is that we say the 4S is lower in energy, okay? So we've done this in the energy diagrams, but it's just a good point to remember that that comes because of their shape, because in the S orbitals, you get these close places next to the nucleus where the electrons can be. And you don't get that with the P and the D orbitals because of their, limited lobe shape. Okay, how is this going to tie in with electron configurations? The biggest thing is that we remember the order that they fill into, but that can be kind of hard to keep that in track. I don't know, maybe it eventually comes pretty natural because you've seen it so many times. But like, let's say we're doing a really big element like iodine, okay? Let's say we want to know, what is that? 50 something, 40? Somebody see that? You guys there? What's iodine, the atomic number? 53. Okay, that's a lot of electrons to put in, right? So I could have an energy diagram. We're actually down to 5 at that point. So I would have to have like 5S would have to be in there and 5P would have to be in there, okay? And then I'd have to put in 53 electrons. That's kind of tedious, okay? So thankfully, quantum mechanics explains and coordinates with the periodic table. And so we can use the periodic table as kind of a cheat sheet for how to identify how the orbitals fill in, and also to know which subshell, like how many electrons are in a given subshell. How to remember that there's 6 electrons in the P subshell, or how to remember that there's 10 electrons in the D subshell. Okay, so I'm going to skip over these right now because I want to do them when we have electron configurations a little more solidified. So I want you to scroll down to, well, it was a lot of slides. Scroll down to this one. So you've got like a full periodic table and they're like color coded. Okay. By the end of today even, you'll be able to look at an element, so I said iodine, you'll be able to look at an element on the periodic table and immediately know that its valence electrons are in n equals 5 and the outermost ones are in the p orbital. And in fact, it's 5p, or sorry, not 5p, p5. So it would be 5p5, okay? So I know it's labeled here. Obviously your periodic table is not labeled, so you're not going to see that. But you're going to be able to identify simply from its location on the periodic table that its outermost electrons are 5p5, okay? So I'm going to show you how to do that. And like I said, it kind of tells you which subshell comes next and then how many electrons there are that fill that subshell. So let's do one that's easier than iodine to start. I think the example includes sulfur, I want to say. Do I care? Let's start with aluminum. Okay, it's a little bit further on, but not too far. So when I look at aluminum, the way I'm going to do this, now if I were to do it on an orbital diagram, it has 13 electrons. All I would do is start at the bottom, because the Aufbau principle tells us to start with the lowest energy, and I would fill in 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that would be aluminum, okay? And if I wanted to give the electron configuration, I would say the subshell, and then I would say how many electrons. So 1s, 2 electrons, 2s, 2 electrons, 2p, 2, 4, 6 electrons, 3s, 2 electrons, and then 3p, 1 electron. Okay, so this shouldn't be that unfamiliar. We did this for a couple simpler atoms as well. You're identifying the subshell, and then you're saying how many electrons are in that subshell. But in order to do that, we had to fill all the electrons in. So let's see how we can use the periodic table to do that a bit more quickly. I gotta get a cough drop because I keep feeling like on the cusp of coughing and it's bugging me. Okay, so when we look at the periodic table, the position where the atom is actually corresponds to its subshell. So each row represents a principal energy level. So the first row here, those atoms that are in that row will have their valence electrons in n equals 1. In the second row, those valence electrons will be in n equals 2. So without even thinking, I can look at fluorine and say, oh yeah, its valence electrons are n equals 2. Very easy, very convenient. And this keeps going this way, n equals 3 and so forth. Okay? The color coding that's listed here corresponds to the subshell of a given energy level. So if it's in the blue section, those first two columns, the subshell of those outermost electrons, or those highest energy electrons, are going to be in the S subshell. The pink ones are going to be in the P subshell. So without even really doing a whole lot more, just recognizing that aluminum's in the third row and it's in the pink section, then I know that aluminum's outermost electrons are in the 3p subshell. And I did not have to go through that whole process of drawing out the orbitals, remembering what order they come in, and putting the 17 electrons in there, or sorry, 13. I just looked at where it was and said it's in the third one, and it's in that P block. Okay? The yellow, the transition metals, those are the d orbitals. So let me show you one real quick. So like we'll just do, I don't know, we'll just do titanium, okay? So titanium, 22 electrons. Would look like this. Okay? In n equal, well, let me get to the n equals 3, but in the D subshell, we'll get to the n equals 3 in a second. Yeah. Yeah, great. Okay, so that was just where I was like, we'll get to that in a second. Why do they drop down a number? Okay, so remember, every time we go up in principal energy level, we add another shape. So we've got the S, then the S and the P, then the SP and the D. That is fine. And normally we would think like, okay, 3S and then 3P and then 3D. So remember that chart that I showed you and this idea of how the shape affects their energy causes the S to fill first. So if it didn't, if the D filled before, this whole block would have to be like shifted. I was gonna say up one, but that wouldn't actually make sense. It would be over on the other side. And that's not how nature works. Like, it doesn't, we don't see the behavior of the atoms does not correspond to something after the energy of those noble gases. It actually goes one layer beyond or one energy level higher. Now, I say one energy level, even though the outer edges are closer in. So in the d orbitals, the edges of the orbital is the same as the 3s and the 3p, but their shape restricts how close the electrons can be. So even though the outer edges are the same, their energy is higher. So the d orbitals will always start at 3, even though they're in the 4th row. So this is the only thing you have to keep in mind when you're doing this, but it's actually a good thing because it reminds you that the S is going to fill first, and then you're going to go to the 3D. So when you do the Ds, you need to remember that N is one less than the column number. And in fact, we won't do any Fs on the test, just to reassure you. We might do some in the homework, but not any on the test. So F is actually 2 less than the column number. And like I said, you have to keep this in mind, but it's really good that it is, or else it wouldn't connect with the, the quantum mechanics. So S's start at 1, which we know they do. P's start at 2, which on the periodic table, it is shifted down, so we know they do. D's start at 3, and F's start at 4. So even though the D is lined up with n equals 4, we know it starts at 3. So we're going to say 4s2, 3d2, which is just what we predicted here. 4s2, 3d2. The only way that we know that is because we know that the 4s is going to fill before the 3d does. Okay? So the electron configuration, I don't have to rewrite this all, but I'm going to have to for room's sake. The electron configuration for titanium, we would expect to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, see, and then I didn't even give myself room, 3d2. Okay, so we even write it after the 4s because we want to indicate that it's actually higher in energy. Okay, so now for aluminum, I think did we go through row by row? I can't remember. I'm going to do this on the next one because I think it'll be easier to see. All right. So aluminum's here. We're going to do that one. And then we'll also do titanium. But we're going to verify these by doing this row by row approach to determine the electron configuration. So what we're going to do is we're going to consider this is the S block, this is the P block, and so forth. we're going to use the row numbers as the n values, and that's going to help us to know the subshells. And then we're going to count the number of elements, and that's going to tell us the number of electrons that are filled into that subshell. Because every time we move an element, we gain a proton, but we also gain an electron too if it's neutral, which we're talking about neutral stuff. Okay? All right, so for aluminum, we're going to start up here at the top, okay? And we're going to say this is n equals 1, and we're in the S block. Now, helium is stupid, so we're going to stick helium over here in the S block where it belongs. They have it color-coded right, but it's just not in the right place. So, n equals 1, S block, 1, 2 elements. Okay, so 1s2. And then that's the end of the row. So we move on to the next row. 2, S block, 1, 2. So 2s2. We go all the way across. We're still in the second row, and we haven't had anything weird yet with the D's. So we're in the second row, and now we're in the P block, and there's 1, 2, 3, 4, 5, 6. This is where you should start to feel little shivers. Like, oh my gosh, how did that work out so perfectly with quantum mechanics and then the periodic table, and the periodic table hadn't even, like, they didn't know anything about this yet. It's because the periodic or the quantum mechanics is a really good model. That's why it works out, because it is explaining all these observations. Okay, so 2p, 6, because there's 6 elements. Next one, 3 in the S block, 1, 2, so 3s2, and then all the way over to the P, 3p1. Okay, so that's my electron configuration of aluminum. Maybe that doesn't seem so much shorter than just drawing the orbital diagram, but if I get down to an element all the way down here, it's going to seem a lot shorter. Okay, I do not want to have to draw an orbital diagram for something that has 100 electrons. Okay, let's do titanium, and then I want to do one that's kind of through that, so we'll do maybe bromine. Okay, titanium, let's just carry on, because that's the cool thing about this, is that the beginning is always the same. So if you're further down the periodic table, it's just going to continue exactly like you did for any other element. It's just going to keep going. Okay, so let's pretend like we didn't stop at aluminum, and we keep going. So now we've hit the 3p, 1, 2, 3, 4, 5, 6. Going to fill that in completely. Then we go down to the next row, 4. It's the S block, 1, 2. So 4s2. Now, there might be that temptation to then say 4d, but where did 3d go? We know that the d orbitals start at 3, so it can't possibly be 4d because we haven't done any d orbitals. Okay, so this is 3d, 1, 2. So titanium, that's its electron configuration, ending in 4s2, 3d2. I don't know if that feels easier to you guys. Hopefully it does, and it doesn't feel like, well, I'd rather just draw the orbital diagram. If you would, by all means, go ahead, if that's easier for you. I think what I like about it is that, like, we're going to do bromine next. When I look at bromine, I immediately know it's going to end in 4p5. Okay? And so even if I just wanted to say the entire valence shell, it's like 4s2, 4p5, done. And in fact, there's an abbreviated way to write this that relies on the noble gases kind of giving us an idea of the core electrons. And so that's also going to make it even shorter. So even though you're going to start by going row through row, maybe by the end of this unit, or certainly when we start doing this in Chem 2 as well, you're going to be able to look at an element and not even really think about how many electrons it has. You're just going to look at its location on the periodic table and its row on the periodic table, and that's going to be able to tell you what its valence electrons are. Okay? All right, let's start clean for bromine. Okay, so starting up at top, 1, S, 2, 2S2, 2P, 1, 2, 3, 4, 5, 6, 3S2, all the way across, 3P, 1, 2, 3, 4, 5, 6, down to the next one, 4 in the S block, 1, 2. Now we hit the D's, okay? So this is a little bit unfamiliar. Remembering that it's 3. Let me shift this so I have more room. Okay. Remembering that it's 3, 3D, and now let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is not coincidence that there's 10 elements and there's 5 d orbitals and each orbital holds 2 electrons. That is just inherent in nature that these things are matching up, okay? So there are 10 available spaces in the D subshell, and that corresponds with each of those 10 elements. So if I looked at any of those elements from scandium through zinc, those ones would all have electrons ending in the 3D subshell. So that's the kind of thing I'm telling you makes it a lot easier, is just by looking at the periodic. Tungsten, W, okay, 74. That one ends in the 5D subshell. Okay, that's useful for me to know. That's going to help me predict things about it. Okay, sorry, finishing on. 3D10. Now we go back to regular N values, 4. 4P, 1, 2, 3, 4, 5. Okay, so 4P5. And that's bromine's electron configuration. Okay, what's the short way? You want to know the short way, believe me. What we're going to do for the short way is we are going to take all of the core electrons, and instead of writing them out, because they don't change, right? Once you are past that noble gas, nothing changes in the core electrons. They just stay close to the nucleus. They don't react. Nothing happens with them. So we don't need to say the same thing over and over again. We can just abbreviate that. And the way we do that is by we take this element. So if we're in bromine, we want to go up one level, but over to the noble gas. So like if we were doing chlorine, we would go to neon. If we were doing fluorine, we would go to helium. So we're going to go to bromine. I'm going to go up to argon. And we're just going to say argon, 4s2, 3d10, 4p5. So what we're saying when we say that is we're saying, hey, do the electron configuration for argon, and then it's the rest of this stuff. So this is the electron configuration for argon. We're substituting in the symbol in brackets. We're substituting in the symbol for those core electrons. Because if you look at where argon is, that would be 1s2, 2s2, 2p6, 3s2, 3p6, which is exactly what we have written up there. So instead of rewriting it, we're just going to write down, hey, think of the electron configuration of argon, and now the rest of this stuff, and that tells us what bromine is. Oh, it's not what I wanted to do. Okay, so let's let you guys practice some of this. So Ooh, we already did bromine. Let's do iron, and then we'll talk about the weirdness of the d orbitals, okay? So I want you to do the full electron configuration for sulfur, and then the abbreviated electron configuration for iron. Okay, so I'll go ahead and write sulfur up here so that when you're ready to check, you can. And in fact, maybe I'll write the abbreviated one just so you can, you know, see another example of how those work.
Would you be able to scroll back to bromine real quick?
Yeah. So the red is the full one, and then the blue is the abbreviated.
I'm good on that one.
Okay. Okay, so I'll go ahead and start iron. That one I'm just going to do the abbreviated. So the way I know the noble gas is just go up one row and then all the way to the end. Okay, just one more minute and then we'll look through these, and also we'll just do another random one where we just kind of like identify its location and show you how you can quickly figure out its electron configuration, especially without even going row by row. Okay, so let's just look at where sulfur is on the periodic table. So it's in the P block. I can identify that immediately. And it's 4 spaces in. So if I just wanted to do the abbreviated one, instead of going row by row, I would say neon, like without even, identifying anything. I'm just going to say neon because it's 1 row above and all the way to the end. And then I'm going to say, okay, I know it's in the 3rd row, so I've got to do the S's first, 3S2, and then 3P4. Okay? So the abbreviated combined with the periodic table approach makes it very quick to see where those valence electrons are, because that's what's coming after that abbreviation is the valence electrons. And now when I talk about sulfur, I'm going to eventually be able to say, okay, like I know now why sulfur is going to accept 2 extra electrons. Remember, we talked a long time ago about how oxygen's column gains 2 electrons in an ionic compound. That's because sulfur has 4 of 6 spots filled in that P subshell. And so it's going to be able to accept 2 more in that low energy subshell. Or when we start talking about covalent bonding next semester, we'll be able to say, okay, I can identify that there's 6 valence electrons really easily. I guess technically you can see that just from the column it's on in the periodic table. It's in the 6th column, so that tells you there's 6 valence electrons. That comes from the fact, though, that the S's are filling and there's 4 filling into the P's. That's why it works out this way, is because in the periodic table, every time we add a new principal energy level, we're going to a new row. Okay, so the last thing we need to talk about today is the fact that the transition metals are really weird. Okay, so let me show you an example. I'm sure I have one here. I want to do chromium, but I was hoping they would have it drawn out. No, I'm going to draw it out for you. So this is the expected electron configuration of chromium. So let's just look at where it's at on the periodic table. So number 24, Cr. So I know it's in the 4th row. So like, I don't really want to think about what's before that. It's argon, but who cares? So 4s2, 4d4. That's what I expect it to be. In reality, chromium actually separates out 1 in each orbital. So if I look at this would be the 4s, and these would be the 5 3d orbitals. So initially, what I would predict is this. But those guys are so close in energy that they actually follow what we typically think of as Hund's rule, where they will separate out each filling 1 orbital so as to minimize electron repulsion. You do not have to know what these exceptions are, okay? I'm not going to expect you guys to know it. If I asked you for the correct electron configuration, I would only be able to, expect you to know the left side, okay? What I do want you to know is that once we get into the d orbitals, because of that closeness of the S and the D, a lot of the times they don't correspond to what we would expect them to be. Okay, that is the reason why, is because the 4s and the 3d, or for that matter, the 5s and the 4d, or the 6s and the 5d, etc., those are very, very close in energy. In fact, sometimes they actually flip-flop. Okay, so the d orbitals end up having bizarre electron configurations or unpredictable ones. And this is why they have bizarre behavior as well. We cannot accurately predict the charges that they will form. Remember, these are those type 2 elements where, you know, chromium forms like, I think, a +3 or a +2. Manganese forms a +6 or a +3. Okay, they have very unpredictable charges that they form. And this is why, because they have this weird thing about having basically 7 different orbitals very, very close in energy. Sometimes you get enough of a separation that they will behave normally the way a main group element would, and sometimes they don't. Okay, so that's what I expect you to know, is that this could happen. The places where it happens is in the transition metals. The reason it happens is because the S and the D end up really close to each other, and that's it. I don't expect you to actually be able to predict what they are, because like we can't even always predict them. A lot of the times, like scientists just have to look at them experimentally and decide. Once you get past the D's though, then they stop behaving that way, which is why things on like the far side of the main group, gallium, selenium, bromine, whatever, iodine, those all, you kind of eliminate the weirdness of the d orbitals once they all get filled in. So for our last example, let's look at, oh, that's actually where we're going to start on Monday. But for our last example, let's just do real quick arsenic, so AS. And you can do the abbreviated one, that's fine. Okay, so once we get past those d orbitals, once they fill in completely, and in arsenic, that's what happens, you fill up that 3D and then you move on to the 4p, then everything behaves as normal. Okay, so it's not just when there's d orbitals filled, it's when the d orbitals are like the highest energy ones that are filled. Once you filled them up, everything's going to act normal. Okay. Try to do all of the homework except for the things that start talking about size, ionization energy, electronegativity, these different properties on the periodic table. We'll talk about those on Monday, but everything up to that point you should be able to do. The homework will be due on Tuesday, so you're getting a jump start. Do you mean, like, clarify more what you mean?
Like when you're doing the electron configuration, it jumps like, cause I like slightly
From 4 to 3, is that what you mean?
from
Or
like 3 to what the I can't think of what the bottom one is.
oh,
Like
the Fs?
yes.
No. So you might see an example in the homework, but I'm not gonna do those on the test.
Okay.
Because it's like 2 less. So like if you were, like, let's say the LA, it would be like 6S2. In fact, that's a terrible example because those ones aren't exactly like they are. But it would be 6S2 and then 4F1.
Okay.
So they jump 2, so I just don't do them on the exams. But
Cause I like
if
we-
you see it in the homework, that's
Okay,
why.
because I know we like I taught my high school teacher like we
Mhm.
did them a little bit and
Yeah.
kind of like I was a little confused on them.
Yeah.
But if I don't,
I know.
remember
Well,
them,
they're
that's-
even weirder than the D's.
Yeah,
Is why we
'cause-
don't mess with them because they're like we could predict them, but they're so far off from the predictions. It's like why bother? Yep.
Thank you.
Hi.
I'm taking the test on Wednesday
Yes.
in class. Or
Yes.
am I gonna do like in the hallway or like?
There's an office down the
Okay,
hall that'll have
okay,
you.
perfect.
Yeah. Do you have a teammate that's doing that as well or no?
I'm not sure.
Not if you. Yeah. If you don't know, then it's probably not. I just thought
Okay.
there was somebody else. So.
Thank you.
Yep.